Hello, in today's video we are going to be taking a look at triple integrals. So we've explored double integrals a little bit, how do we use them to calculate volume and area. So the next logical thing, of course, is going to be triple integrals. So this is what we've done so far. We've looked at some region in the xy plane, we've mapped it up onto some function of two variables, and then we've used a double integral to calculate either the volume underneath that graph or the surface area on that portion of the graph. Now, we said this region in the xy plane, which sometimes we call D, sometimes we call R, doesn't really matter, but we said that that region had to be closed, which means we can draw a rectangle around it. And so then we took the limit as n went to infinity, and again, our main, or the first application we learned, is to find the volume underneath F. So what we're going to be doing today is we're going to be doing triple integrals. So instead of having a region in the xy plane, we're going to have a 3D region, and we're going to call that region B. That region has to be closed, which three-dimensionally means that it can be contained within a box. So we have this region, we're containing it in a 3D box, and we're going to divide it into n sub-boxes. So then what we are doing is we are looking for the volume of each box, that's delta V of k, and this just represents any point in the box. So what we're doing then is we're taking the volume of each box and we're multiplying by the function value of that box and taking the limit as n goes to infinity. When we do, what that gives us is the triple integral over the region B of f of x, y, z dv. And so the question is, why do we care about that? What does a triple integral practically mean to us? What it gives us is what we call hypervolume. So a double integral gives us volume, a triple integral gives us hypervolume. It has the same properties and evaluation as a double integral. So then one just quick tidbit is if our B is really nice and it's a box where x is between two values, y is between two values, and z is between two values, then when you set up that triple integral, you're integrating with respect to your x, y, and z with those limits of integration. So that is when you have some nice rectangular coordinates, but that will not always be the case, of course. So let's jump right in and look at a few examples. So here's our first example. Evaluate this triple integral where g is the region where x is between 0 and 1, y is between -1 and 2, and z is between 0 and 3. So setting this up, we're going to have the triple integral of x, y, z squared, and then we need to decide the limits of integration. I will tell you that convention is to do z and then y and then x. So this is convention. That will not always be the case though, and of course we'll see some examples where that's not going to be the case. So our z goes from 0 to 3, our y goes from -1 to 2, and our x goes from 0 to 1. Okay, and then we're integrating this exactly the same as we did before. So we're going to integrate with respect to z first, which means that x and y are just constants. So these integrals are going to remain the same. And then we end up with 1/3 x, y, z cubed, and we are evaluating from z equals 0 to z equals 3, and then we have dy dx. Like we did with double integrals, I highly suggest you write z equals so that you remember you're substituting for z and not x or y. If you do that initial substitution, if we substitute 3 in, 3 cubed is 27, and we take 1/3 of that, we're going to get 9xy. So now we're integrating with respect to y. So again, just this integral right here. So x is just a constant. When we do that, we're now integrating from 0 to 1, and we have 9/2 xy squared, evaluating from y equals -1 to y equals 2. So what that gives us then is if I take out the 9/2, and I have 0 to 1, I'm going to get 4x subtract 1x dx. So this gives me 9/2 integrating from 0 to 1, 3x dx. And if you trust me, I'm going to tell you that answer ends up being 27 over 4. Okay, a quick reminder for you of something that you can do. If your region is rectangular, and so by rectangular we mean something like we have above, so x is between two numbers, y is between two numbers, and z is between two numbers, and the function is a product. So what we mean by that is that we can write f of x, y, z in terms of a function of x multiplied by a function of y multiplied by a function of z. Then we can split up the integral. So what we could have done from the very beginning when we were evaluating this interval, or integral rather, we could have written that instead as the integral from 0 to 1 of x dx multiplied by the integral from -1 to 2 of y dy multiplied by the integral from 0 to 3 of z squared dz. So that might have been a little bit kinder with our simplifying or our integrating, but we got to be careful with this. You have to make sure, A, that you have rectangular coordinates, so x, y, and z are between two constants, and you have to have a function that can be written as a product of three different functions. Okay, so moving on. This was a very kind triple integral because these limits of integration were so nice. As you remember before with double integrals, that's not always going to be the case. So we're not always going to have a solid that is a prism like this one is. So that's what we're going to take a look at now, is what happens with just general figures. Like before, if you remember with double integrals, we talked about type 1 and type 2 solids, and I told you that I didn't really love that vocabulary, that it wasn't helpful to me, but we went over it anyway. Well, with triple integrals, there's the same thing. There's type 1, type 2, and type 3 solids. So again, we're going to talk about what those solids practically mean, and then I'm going to tell you how I set integrals up. So a type 1 solid is you have a solid where your upper surface, z, can be written as a function of x and y, and you have a lower surface that can be written as a function of x and y. So we see that right here. So we're integrating over this region E. So triple integral over this region E. So then if we want to figure out what our dv looks like, what our limits of integration would be, we would have, still as a triple integral, and we have f of x, y, z. But what we would end up doing is integrating with respect to z first from that lower function to that upper function. And then what we would do is dA means we then have to figure out the limits with respect to x and y. So what remains is integrating with respect to x and y. So what we do is we take that figure and we project it down onto the xy plane for this region D, and that region D helps us find our limits of integration for x and y. So in general, how we're going to find limits of integration, we're going to find the upper and lower surfaces bounding our surface. Those are going to be our limits for z. Then we are going to project onto the xy plane. So we're going to project E onto the xy plane, which gives us our figure D, which will then treat like a double integral, helping us find our limits for x and y. So I think this is most helpful if we just look at an example. So let's take a look at example 2. We're evaluating this triple integral where t is the tetrahedron bounded by x equals 0, y equals 0, z equals 0, and x plus y plus z equals 1. Okay, so first thing, you're going to have to be able to sketch this. And so those quadric figures that we looked at the very beginning of Calc 3, those are going to be so important. So you might have to go back and review them, but you're going to have to remember exactly what all of these look like. Now, x equals 0, y equals 0, z equals 0, those are all planes. That's telling us we're looking in the first octant only. And then x plus y plus z equals 1, this is also a plane. So, drawing ourselves a little sketch, we're looking in the first plane, or the first octant only. This is a portion of that plane. Okay, so we're going to have a triple integral, and I'm giving myself some room. Okay, so in this case, our z, if we want to integrate with respect to z first, it goes from 0 to the plane. So you're going to have to be able to visual that. It's a little hard for me to show you, but we start on the xy plane and we go up until we hit this plane, x plus y plus z equals 1. So to find the upper limit of integration for z then, I'm going to solve and I get z is 1 minus x minus y. Then we need to find the limits of integration for x and y. And so what we're going to do now is look at the xy plane. So that is right here. So this then is our region above that we called the region D. So what I would suggest is that you sketch this in the xy plane so that we're looking at a 2D figure instead. So this is what we are looking at now is our region D. Now in this case, it doesn't matter if we integrate with respect to x or y first. Generally, we'll do y and then x if we can. So y is going to go from 0 to the line, and that is the line y equals 1 minus x. And x is going to go from 0 to 1. Now, a quick tip to make sure that your triple integral makes sense. Your outer integral always has constants. So you should never have a variable in your outer integral. So again, what this gives us a hypervolume. Now, I know you're going to come to class and ask me, practically, what does that mean? And I don't have an answer for you. Okay, so what I really wanted us to do was just set this one up. If you want to solve, go for it. Just pause the video and practice yourself. I will let you know the answer ends up being 1/24. Okay, so that was the first type of solid. There's two more we're going to take a look at, and then we'll take a look at a few more examples. So the next two we have are type 2 solids and type 3 solids. So sometimes you have lateral surfaces that are bounding the figure, not top or bottom. So what we do if we look here, we can write x as a function of y and z, as a function of y and z. So if this was our solid, what we're going to do then is we're going to integrate with respect to x first. What we do then is project E onto the YZ plane to give us our 2D figure, which would give us our outer limits of integration. Type 3 solid is a similar idea. You can write y as a function of x and z, and then you're projecting onto the xz plane to find those limits of integration. Again, I don't think type 2 and type 3 solids are helpful vocabulary. I think what is most helpful is to draw a picture and see what's going on. And so that's what we're going to take a look at now, is I'm going to show you my thought process as I go through a triple integral. So let's take a look at this example number 3. Evaluate this triple integral where E is bounded by y equals x squared plus z squared and y equals 4. Okay, so you're going to have to know what these figures look like. You have to know what these figures look like. Because if you don't, it's going to be very hard to set up your limits of integration. So y equals x squared plus z squared is going to be a paraboloid. And y equals 4 is going to be a plane. So if we go to sketch this out for ourselves, at y equals 4, I'm going to have x squared plus z squared equals 4. So that will give me a circle. And then here is my paraboloid. Okay, so we set up our triple integral. So we have to figure out our limits of integration. Now, we have a little hint here in that we have y equals and y equals. So y is written as a function of x and z. Now, if we look at our figure, if we start at y, it starts at the paraboloid and it goes towards the plane. And that is always the same. That's always consistent. It's always starting at the paraboloid and going to the plane. So we can start by integrating with respect to y. Y starts at the paraboloid, so x squared plus z squared, and goes into the plane, which is 4. So now, to figure out our limits for x and z, what we do is we project our figure onto the xz plane. And so what we do is we end up with this circle. And that is the circle x squared plus z squared equals 4. So in this case, it doesn't really matter which one I integrate with respect to first because we have a circle. So I'm going to do z and then I'm going to do x. My limits for z then are going to be negative square root of 4 minus x squared to positive square root of 4 minus x squared. And x goes from -2 to 2. Okay, so at this point, we're going to start with our integration. So we're going to integrate with respect to y first, which means that entire square root is just a constant. So we're going to have this -2 to 2, this negative square root of 4 minus x squared to positive square root of 4 minus x squared. And then we have y, square root of x squared add z squared, from y equals x squared add z squared to y equals 4, dz dx. Okay, so then that gives us this -2 to 2, negative square root of 4 minus x squared to positive square root of 4 minus x squared. And then we have 4 subtract x squared subtract z squared times that square root of x squared add z squared, dz dx. So maybe that occurred to you, and if it did, that's great. Now, the polar that we did before was in terms of x and y. We can still do polar in terms of x and z. In the integral that we currently have, r squared will be x squared add z squared. Okay, so let's keep this going then. So when we switch to polar, this is going to be 4 subtract r squared times r, and then you have to remember. So first of all, this r comes from there. You have to remember, as soon as you switch to polar, you're going to get another r, dr d theta. So make sure you don't forget that extra r. Okay, so now our limits of integration for r, our radius goes from 0 to 2, and theta goes from 0 to 2 pi. Okay, and then that's what you would keep doing. Now, I'm not going to go through the integrating of this because we've done a whole lot of integrating, but if you would like to, go for it. I will tell you, if you would keep solving, you would get 128 pi over 15. Okay, so my advice is when you're trying to figure out your order of integration and your limits of integration, you gotta start with a picture. So start with a picture and then look like we did before. Is there a way for me to easily find the limits for z? Does my lower bound and upper bound stay the same for z? Yes or no? Okay, what about y? What about x? And that's how you figure out your initial order of integration. And then you'll look at your 2D projection to figure out the dA part. This is tricky, but we'll get a lot better with some more practice. So now that we have our introduction to triple integrals and using them for hypervolume, let's move on to one more application. Okay, so if you remember, we used double integrals to calculate mostly volume underneath a curve, but we also could use them to find area, which means then we can use triple integrals to find volume. Similar idea to double integrals. It's going to be the triple integral over your surface of 1 dv. Okay, so let's take a look at this next example where we're just going to set it up. We're not going to go through the actual calculation. Find the volume of the wedge in the first octant that is cut from the solid cylinder, y squared plus z squared is less than or equal to 1, by the planes y equals x and x equals 0. Okay, so this is not going to be the prettiest picture to draw, but hopefully you get the idea. Okay, before I draw that cylinder, I'm going to draw that line y equals x. So it's really a plane, but that is what is cutting out the part of our cylinder. So then we have this wedge that goes from here, and it goes to here. So this is 1, So this is the volume of the wedge that we are looking at. So that's what we have to be able to figure out how to set up. So we're going to set up volume as a triple integral. So here is my suggestion. My suggestion when you're setting up your limits of integration is to try z first. Okay, so like I said, convention is dz, dy, dx. So I would try z first. Now what we notice is we are starting from the xy plane. So if we're looking at the z direction, it's always going from this plane up until the cylinder or up until the wedge. So what we can do then is we can say that z goes from 0 to the square root of 1 minus y squared. So then to figure out our limits of integration for x and y, we have to look at our projection, which is this part right here. So that is our region D. So if I were to look at a 2D picture of that, it looks like this. So that means if we do x next, x is going to go from 0 to the line, 0 to the line, 0 to the line. So we get 0 to y equals x, and x is going, or y is going rather, from 0 to 1. And then you could integrate this. I'm not going to, you could. So, question I have for us is, what if we integrated with respect to x first? So we're going to do 1, we're going to integrate with respect to x first. Okay, so looking at our figure, if we start at the xy plane, we're going from x is 0 to the line, right? X is 0 to the line, and as we go up, that continues to be the case. We continue to go from x is 0 to our line y equals x. And then maybe we want to go with respect to z and y. Okay, so if we're going to do that, we need to find our projection. So we need to find the projection on the YZ plane. So looking at our figure, that would be this part here, which is this circle, y squared plus z squared equals 1, which means z is going from 0 to the square root of 1 minus y squared, and y is going from 0 to 1. So we can see here, we easily could have integrated with respect to x first instead of z. What I want us to notice, though, is all we did was switch around the order and switch the limits of integration. When we switched the order, though, it didn't switch the limits of integration. That's not always the case. So please don't think willy-nilly that you can just switch the order of integration and keep all limits of integration the same. That's not the case. Most of the time, that will not work. So let's write a quick note about that. It's not always the case that we can flip the order without changing the bounds. Okay, so together we are going to take a look at one more example, again, just setting it up, we're not solving, to find volume. Find the volume of the solid enclosed between the paraboloids, z equals 5x squared plus 5y squared, and z equals 6, subtract 7x squared, subtract y squared. Okay, so I'm going to start by setting up this volume. My limits of integration are going to be big, so I'm going to give myself some room. First thing you should hopefully be able to tell is that we're going to integrate with respect to z first. So this is going to start at the origin and open up. This one will open down. So we're integrating from 5x squared plus 5y squared to 6 subtract 7x squared subtract y squared. The problem is, what does our projection look like? So what does our region D look like? How do we find the limits for y and x? So to find our projection, so our region D or R, whatever you want to call it, that's going to happen where these two figures intersect. So we get 5x squared plus 5y squared, is equal to 6 subtract 7x squared subtract 7y squared. So I'm moving everything to one side. This gives me 12x squared add 6y squared is equal to 6. Or 2x squared add y squared is equal to 1. So hopefully we know what this looks like. This is an ellipse. Y-intercepts of 1, x-intercepts of 1 over root 2. So this case, it doesn't matter if you integrate with respect to x or y first. Because I didn't give myself a ton of room, I'm going to rewrite this. So I'm going to choose to integrate with respect to y first and then x. Like I said, it doesn't really matter. Integrating with respect to y, if we solve for y, we're going to get plus or minus the square root of 1 minus 2x squared. So we know we're going from the bottom part of the ellipse to the top. So we are going from negative the square root of 1 minus 2x squared to positive the square root of 1 subtract 2x squared. And then if we look at our limits for x, we're going from here to here. So we're going from negative 1 over root 2 to positive 1 over root 2. Now, I just wanted us to set this one up. We're not actually going to integrate. Those look like pretty rough limits, so we're just going to leave it there. Now, if we were to continue with this triple integral, this would give us a volume. Okay, so I know this was a lot. What is trickiest is figuring out those limits of integration, and right now it's hard, but it'll get a lot better with some practice. So thank you for sticking with me. Moving forward, like we did with double integrals, we looked at using polar. We're going to do something similar here with triple integrals, is we're going to look at another coordinate system in the next video, the next two videos actually, that make integrating sometimes easier. So thanks for sticking with me, and I'll see you in the next video.